Imagine your store launches a flash sale. 1 million orders arrive in minutes. In the last episode, we said Kafka stores events in a topic that behaves like an append-only log. But now there's a problem. If a topic is just one giant log on one server, eventually that machine becomes the bottleneck. One disk, one network card, one CPU. Even sequential writes have limits. Kafka solves this by changing the shape of the topic itself. A topic is not one log, it is many logs called partitions. The orders topic might have 3 partitions, or 30, or 300. Each partition is its own independent append-only log, and those partitions can live on different servers called brokers. So instead of one machine handling every write, the load spreads out across the cluster. One producer writes to partition 0, while another writes to partition 1 at the exact same time. Add more partitions across more brokers, and you add more disks, more network bandwidth, and more parallel writes. That is horizontal scaling, and it is the reason Kafka can handle enormous traffic spikes without collapsing. But partitioning creates a new question. When the checkout service publishes an event, how does Kafka decide which partition receives it? If the event has no key, Kafka spreads records across partitions evenly, almost like dealing cards. That keeps the workload balanced. But balancing alone is not enough, because sometimes order matters more than distribution. Take order 42. Over its lifetime, it generates several events: order placed, payment received, order shipped. If those events land in different partitions, consumers may process them at different speeds. One consumer could read shipping before another even reaches payment. That's where message keys come in. If every event for order 42 uses the same key, Kafka hashes that key and always routes those events to the same partition. Same key, same partition, every time. Inside a single partition, Kafka preserves strict ordering. Events are read in the exact sequence they were written. That leads to the most important rule in Kafka ordering. Order is guaranteed within a partition, never across partitions. Partitions give Kafka write scalability, but now reading becomes the next challenge. Imagine one consumer trying to process 300 partitions alone. It would drown under the workload. Kafka solves this with consumer groups. A consumer group is a team of consumers working together as one logical application. Suppose the shipping service runs 3 instances inside the same group. Kafka divides the partitions among them. Maybe consumer 1 gets partitions 0 and 1, consumer 2 gets partitions 2 and 3, consumer 3 gets the rest. The key rule is that inside a group, each partition is assigned to exactly one consumer at a time. That prevents duplicate processing within the team, while still allowing parallelism. And the group is elastic. During the flash sale, traffic spikes, you launch more consumers, Kafka automatically rebalances the partitions across the larger team. If a consumer crashes, Kafka detects it and reassigns those partitions to surviving members. Consumers track their position using offsets, which are basically bookmarks inside the log. So when ownership moves to another consumer, processing resumes from the last recorded offset instead of starting over. Now comes the feature that makes Kafka feel fundamentally different from a traditional queue. Multiple consumer groups can read the same topic independently. The shipping service reads the orders topic, the analytics service reads it too, fraud detection also reads it. Each group keeps its own offsets, so they all move through the same event stream at their own pace without interfering with one another. There's one important trade-off, though. The number of partitions limits the maximum parallelism of a consumer group. 10 partitions means at most 10 active consumers. Any extras sit idle. So partition count is not a random configuration. It directly shapes throughput and scaling. So the full picture looks like this. Topics are split into partitions so writes can scale across brokers. Keys keep related events together and ordered inside one partition. Consumer groups divide partitions across many workers to scale reads, and multiple groups can consume the same data independently. That's how Kafka survives a flash sale without breaking a sweat.